Welcome back to the Deep Dive, your shortcut to being well-informed. Today, we're diving into something pretty huge, a conceptual history of, well, everything, the universe. We're digging into source material that maps our understanding from, a fixed Earth right at the center of it all, up to the big theoretical clash still puzzling physicists today.
It's a massive undertaking, really, and the work we're drawing on, it became this global sensation. I mean, think about it. A book on cosmology hitting the Sunday Times bestseller list for 237 weeks, translated into 40 languages. It just shows how much people want answers to those fundamental questions. Like, where did we come from? Why is the universe like this?
Exactly. So our mission today is to unpack those key moments, those intellectual leaps that totally changed how we see the cosmos. But crucially, we need to keep coming back to that tension, that core conflict in modern physics.
Right, because that incompatibility is really the heart of the matter, isn't it? You've got these two incredible theories from the 20th century, both stunningly successful in their own domains, but they just don't play nice together.
Okay, so let's set them up. On one side, we have general relativity, Einstein's masterpiece. It gives us gravity, the shape of space-time, the universe on, the grandest scales. Planets, stars, galaxies, black holes.
The really big stuff. And then, on the other side, you have quantum mechanics. This theory absolutely dominates this super small scale. We're talking atoms, particles, forces operating over ridiculously tiny distances. But when you try to combine the math from both, often it just breaks. You get infinities, answers that don't make any physical sense.
Yeah, nonsense predictions. So, the hunt for that single theory, that quantum theory of gravity that merges the big and the small, that's the dream, right?
That's the holy grail of theoretical physics, pretty much. And understanding how we got to this point, this conflict, is key to seeing the path forward.
Okay, let's start at the beginning then, or at least our understanding's beginning.
Right. We have to appreciate just how long the old models lasted. For almost 2,000 years, the dominant view, coming mostly from Aristotle and later formalized by Ptolemy, was a small, unmoving Earth right in the middle.
And Aristotle, back in the 4th century BC, he wasn't just guessing, was he? He actually had observational arguments for a round Earth.
He did. Pretty clever ones, too. 3 main ones. First, if you travel south, the North Star appears lower in the sky. That only works on a curved surface. Second, watching ships approach shore, you see the sails first, then the hull. Again, curvature.
Simple but effective. And the third one?
The Earth's shadow on the moon during a lunar eclipse. It's always curved, always round. If Earth were a flat disk, that shadow would sometimes be, a line or an oval, depending on the angle, but it's always circular.
So he nailed the shape. He even tried to estimate the size, didn't he?
Yeah, he came up with about 400,000 stadia for the circumference. Turns out that was roughly double the actual size, but still an impressive attempt for the time.
Okay, so shape, round, but location and motion. Completely wrong by our standards. He thought Earth was fixed.
Absolutely fixed. Stationary. And everything else, sun, moon, planets, stars, they all moved around us in perfect circles. That perfection, the circle, was, almost a mystical requirement. Heavenly bodies had to move in flawless paths.
Which is where Ptolemy comes in, much later, in the 2nd century AD, because the planets don't look like they move in simple circles, do they? They do that weird backward loop sometimes.
Retrograde motion, yeah.
Right.
That was the big problem for the simple model. So Ptolemy kept the Earth at the center, but he added layers of complexity to make it work. He imagined Earth surrounded by 8 nested transparent spheres. 1 for the moon, 1 for the sun, 5 for the known planets, then Mercury, Venus, Mars, Jupiter, Saturn, and 1 for the fixed stars.
Okay, spheres. But how did that explain the looping?
With epicycles. Little circles whose centers moved along the main big circles, the spheres. So a planet would orbit on its epicycle, while the epicycle itself orbited the Earth on the larger sphere. It created these complex, loopy paths that actually matched observations reasonably well.
Reasonably well.
Yeah.
But it sounds incredibly complicated. Like, really contrived.
It was. Geometrically clever, but cumbersome. And it had known flaws. Like, it predicted the moon should sometimes look twice as big as it actually does, depending on where it was on its epicycle, which obviously it doesn't.
Yet this model stuck around for over 1,000 years.
It did. Partly because it worked well enough for predictions like navigation and astrology, which were important then. And partly, maybe mostly, because it fit the philosophical and religious views of the time. It provided a neat cosmic structure with Earth and humanity at the center. Plus, it conveniently left space outside the outermost sphere of stars for, heaven and hell.
A place for everything.
Yeah.
Okay, so when did things really start to shift?
The first major crack appears in 1514, Nicholas Copernicus. He proposed a much simpler idea. What if the sun is at the center? He realized that if the Earth orbits the sun, then that weird retrograde motion of planets like Mars is just an optical illusion. It happens when the faster-moving Earth overtakes a slower-moving outer planet in its orbit.
Much cleaner explanation. But he was nervous about publishing it, right?
Extremely nervous. He knew it went against centuries of accepted wisdom and, crucially, church doctrine. He only published the full theory near his death, and his initial ideas circulated anonymously. He feared being accused of heresy.
So the idea was out there, but it needed proof. Real observational evidence.
Exactly. And that came spectacularly in 1609 with Galilei and his telescope. He looked at Jupiter, and what did he see? Moons. Little points of light clearly orbiting Jupiter itself. This was huge. It directly contradicted the Aristotelian idea that everything must orbit the Earth. Here was clear proof that some things orbited another planet.
A mini solar system around Jupiter. That must have blown people's minds.
It certainly shook the foundations, but there was still a problem even with the sun-centered model. Both Copernicus and Galileo still clung to the idea of perfect circular orbits.
Ah, the obsession with circles again.
Right. It took Johannes Kepler meticulously analyzing the incredibly precise astronomical data gathered by Tycho Brahe to crack that one. Kepler found the planets didn't move in circles at all. They moved in ellipses, with the sun at one focus of the ellipse.
Ellipses, finally matching the data. But Kepler himself wasn't thrilled about it.
Not aesthetically, no. The source material mentions he found the idea of ellipses kind of repugnant. It lacked that perfect divine symmetry of the circle he still believed should govern the heavens. He had the correct mathematical description of the paths, but he didn't really have the why ellipses.
Okay, so we need the why. Enter Newton.
Enter Isaac Newton, yes. His Principia Mathematica, published in 1687, is arguably the single most important scientific book ever written. It provided the why. First, his laws of motion completely changed the game. Aristotle thought things naturally wanted to be at rest.
Yeah, you had to push something to keep it moving.
Newton showed that's wrong. An object in motion stays in motion in a straight line at constant speed unless a force acts on it. Rest isn't special. Force doesn't cause motion, it causes acceleration, a change in speed or direction.
That's fundamental shift number one. And then came the big one.
Universal gravitation. The idea that every object in the universe attracts every other object. The strength of that attraction depends on their masses. More mass, more pull, and crucially, it decreases with the square of the distance between them. Double the distance, the force drops to a quarter.
And this single law explained, well, everything.
Pretty much everything related to motion and gravity known at the time. Why apples fall down, why the moon orbits the Earth, why the planets orbit the sun, and why those orbits are elliptical, as Kepler found. Newton showed mathematically that his law of gravity naturally produces elliptical orbits for bodies orbiting a central mass like the sun.
It unified celestial mechanics and terrestrial physics. One set of laws for heaven and earth.
Exactly. That famous story about the apple falling while maybe not literally hitting him on the head captured the essence of his insight. The same force pulling the apple down is holding the moon up. It's universal.
Okay, so Newton gives us this clockwork universe governed by precise mathematical laws. But even Newton held on to one old idea, didn't he? About time.
Yes, both Aristotle and Newton, despite their differences, believed in absolute time. They assumed that the time interval between any two events would be measured as exactly the same by any observer anywhere in the universe as long as they had accurate clocks. Time flowed universally like a cosmic river, independent of anything else.
Before we get to shattering that idea, you mentioned Galileo challenging Aristotle earlier, not just on location, but on method.
Right. Aristotle believed you could figure out the laws of nature mostly through pure thought logic. Galileo was all about observation and experiment. Aristotle thought heavier objects fall faster. Galileo, legend has it, dropped weights from the Leaning Tower of Pisa, or more verifiably, rolled balls down inclined planes. He showed that, ignoring air resistance, all objects accelerate downwards at the same rate, regardless of their weight. That was a huge step towards experimental science.
Like the feather and hammer drop on the moon during the Apollo missions.
Precisely. Perfect demonstration. But back to time. The first real hint that time might not be so absolute came before Newton's Principia, actually.
Oh, who was that?
A Danish astronomer, Ole Romer, in 1676. He was observing the moons of Jupiter, specifically timing when they disappeared behind Jupiter their eclipses. He noticed the timing wasn't perfectly regular. The eclipses seemed to happen later when Earth was farther away from Jupiter in its orbit, and earlier when Earth was closer.
So the travel time of the light itself was making the difference.
Exactly. Romer correctly figured out that the delay was the extra time it took light to cross the increased distance between Earth and Jupiter. This was the first real proof that light doesn't travel instantaneously. It has a finite speed. His estimate was about 140,000 miles per second, not bad for the 17th century. The actual value is closer to 186,000 miles per second.
Okay, so light has a speed limit. That's established. How does that connect to breaking absolute time?
The next crucial piece came much later, in 1865, with James Clerk Maxwell. He unified the theories of electricity and magnetism. His equations predicted the existence of electromagnetic waves, things like radio waves, visible light, and crucially, they predicted these waves must always travel at a specific, constant speed. The speed of light.
Always. Regardless of how fast you're moving when you measure it.
Yes. And that's the kicker. That constant speed of light created a massive problem for the idea of absolute time and absolute space. Think about it. Speed is distance divided by time. If everyone, no matter how they're moving, must measure the speed of light to be the exact same constant value.
But they are moving relative to each other, so they would measure the distance. The light travels differently.
Then the only way for the speed distance time to remain constant for everyone is if their measurements of time also differ.
Whoa. So my clock and your clock would literally tick at different rates if we were moving relative to each other, just so we both see light moving at c.
That's the unavoidable conclusion. It was Albert Einstein in his 1905 theory of special relativity who fully embraced this. He showed that because the speed of light is constant for all observers, space and time cannot be absolute and independent. They are relative and interwoven into a single fabric. Space-time. Each observer has their own personal measure of time. The idea of a universal, absolute clock ticking away for everyone, gone, shattered.
That is just fundamentally weird. So that's special relativity. What about general relativity 10 years later?
Special relativity dealt with constant velocity. General relativity, Einstein's 1915 theory, incorporated acceleration and, crucially, gravity. Before GR, space and time were seen as a fixed, passive backdrop, like a stage where the play of the universe unfolds. The stage itself wasn't affected by the actors.
But GR changed that.
Dramatically. GR says space-time isn't passive, it's dynamic. It's a flexible fabric that is warped and curved by the presence of mass and energy. And it's this curvature of space-time that we perceive as gravity. Objects don't pull on each other through empty space. They follow the curves in space-time created by mass. Like a bowling ball on a trampoline warping the surface, causing marbles nearby to roll towards it.
So gravity isn't really a force in the Newtonian sense, it's geometry.
In essence, yes, it's the geometry of space-time. And this radical idea made a testable prediction. Einstein predicted that the huge mass of the sun should warp space-time around it enough to actually bend the path of starlight passing nearby.
Bend light? How could they even test that? You can't see stars near the sun normally.
Right, you need a total solar eclipse. When the moon blocks the sun's disk, you can briefly see the stars close to the sun's edge. In 1919, a British expedition led by Sir Arthur Eddington did exactly that. They photographed the star field around the sun during an eclipse.
Did the stars look shifted?
They compared the positions to photos of the same star field taken when the sun wasn't there. And yes, the stars whose light had passed near the sun appeared slightly shifted outwards away from the sun. The amount of deflection matched Einstein's predictions from general relativity almost perfectly. It was a stunning confirmation. Space and time are dynamic and warped by mass.
Okay, so space-time is this dynamic thing. Meanwhile, astronomers were figuring out just how big this stage actually is.
Absolutely. While the theorists were revolutionizing space and time, observers were grappling with cosmic distances. The first step was stellar parallax. As the Earth orbits the sun, nearby stars seem to shift their positions slightly against the backdrop of very distant stars. By measuring that tiny shift angle, you can calculate the distance.
Kind of like holding your finger out and closing one eye. Then the finger seems to jump against the background.
Exactly the same principle. But the shifts for stars are minuscule, showing how incredibly far away they are. We measure distances in light years, the distance light travels in a year. The nearest star, Proxima Centauri, is over 4 light years away. Our sun is only 8 light minutes away. The scale is just staggering.
And for a long time, we thought our collection of stars, the Milky Way, was basically it, the whole universe.
Pretty much. By the 18th century, Philosophers like Kant and astronomers like Herschel realized the Milky Way was a vast, flattened disk of stars. But the nature of those faint, fuzzy patches called nebulae was hotly debated. Were they gas clouds inside our galaxy or something else entirely?
Enter Edwin Hubble in the 1920s.
Right. Working at the Mount Wilson Observatory with its powerful telescope, Hubble made two revolutionary discoveries. First, he managed to find specific types of stars called Cepheid variables inside some of those nebulae, particularly the Andromeda Nebula.
And why were Cepheid variables important?
Because their brightness varies in a very predictable way that's directly linked to their true intrinsic luminosity, how bright they actually are. So if you measure how rapidly a Cepheid pulsates, you know its true brightness. Then you measure how bright it appears in the telescope. Comparing the two tells you how far away it must be. Like knowing the wattage of a distant light bulb lets you estimate its distance based on how dim it looks.
Standard candles.
Yeah.
Okay. So he measured the distance to Andromeda.
And found it was vastly farther away than any star within the Milky Way. Andromeda wasn't a gas cloud, it was another entire galaxy, an island universe like our own, probably even bigger. He went on to show many other nebulae were also distant galaxies. Suddenly, the universe wasn't just the Milky Way. It contained hundreds of billions of these galaxies, each with hundreds of billions of stars.
That just completely dwarfs our sense of place in the cosmos. An unbelievable expansion of scale.
It was profound. But Hubble wasn't done. His second major discovery came from analyzing the light from these distant galaxies. Astronomers use spectroscopy, splitting light into its rainbow of colors to see the chemical composition of stars and galaxies. Elements absorb specific wavelengths, leaving dark lines in the spectrum like a barcode.
So you can tell what stars are made of from their light. What did Hubble find with galaxy spectra?
He found the expected patterns of lines, confirming they were made of familiar elements. But the patterns were consistently shifted towards the red end of the spectrum. The farther away the galaxy, the bigger the redshift.
Redshift, like the Doppler effect for light.
Exactly like the Doppler effect. We hear it with sound. An ambulance siren sounds higher-pitched, shorter wavelength, coming towards you, lower-pitched, longer wavelength, going away. With light, moving away shifts the light towards longer, redder wavelengths, redshift. Moving towards us shifts it to shorter, bluer wavelengths, blue shift. Since almost all distant galaxies showed redshift, it meant they were almost all moving away from us.
And the farther away, the faster they're receding.
That's Hubble's law. The recession velocity is proportional to the distance. The universe isn't static, it's expanding.
Wow. Was this predicted? Or was it a complete surprise?
Amazingly, it was predicted theoretically, even before Hubble's observations confirmed it. Back in the early 1920s, a Russian physicist named Alexander Friedman had worked out solutions to Einstein's general relativity equations that described an expanding universe.
Based on what assumptions?
Two big ones about the universe on large scales. First, that it's isotropic. It looks roughly the same in every direction from our viewpoint. Second, that it's homogeneous.
Yeah.
It looks roughly the same from any viewpoint, from any galaxy. We don't occupy a special central position. The source material calls this the assumption of modesty.
Makes sense. We keep learning we're not the center of things. So Friedman's model predicted expansion.
Yes. His solutions showed that a universe filled with matter, as described by GR, should naturally be dynamic, either expanding or contracting. A static universe was unstable. The expansion isn't like an explosion into space. It's an expansion of space itself, like points on the surface of an inflating balloon all moving away from each other, but with no single center on the surface.
That perfectly explains Hubble's law, everything moving away from everything else. But didn't this idea of an expanding universe implying a beginning face resistance?
Oh, absolutely. Many scientists, including Einstein initially, preferred the idea of a static, eternal universe. The concept of a definite beginning sounded too much like religious creation stories for some. It needed more direct evidence.
Which came accidentally.
Completely accidentally, yes. In 1965, two radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, were working with a very sensitive microwave antenna. They kept picking up this faint, persistent background hiss, like static, coming equally from all directions in the sky, day and night, no matter where they pointed the antenna.
It couldn't get rid of it.
Nope. They checked everything. Equipment malfunctions, interference from New York City, even famously cleaned out pigeon droppings from the antenna horn, thinking the white dielectric material might be the source. Still there.
So what was it?
They'd found the cosmic microwave background radiation, the CMB. Theoretical physicists nearby at Princeton, like Robert Dicke and Jim Peebles, realized Penzias and Wilson had found the predicted afterglow of the Big Bang. It was the leftover heat radiation from the incredibly hot, dense early universe, now cooled and stretched by the expansion of the universe over billions of years into microwaves.
The echo of creation. That must have sealed the deal for the Big Bang model.
It was incredibly strong evidence. The fact that the CMB is almost perfectly uniform in all directions confirmed Friedman's assumption of isotropy on the largest scales. Then, much later, in 1992, the Komuvi satellite measured tiny temperature fluctuations in the CMB, just 1 part in 100,000.
Tiny ripples. Why were they important?
Because a perfectly smooth early universe wouldn't lead to the clumpy structure of galaxies and clusters we see today. Those tiny fluctuations were the seeds. They were minute density variations that gravity could then amplify over billions of years, pulling matter together to form the first stars and galaxies. The fingerprints of creation, as they were called.
Okay, so the evidence overwhelmingly points to an expanding universe that began in a hot, dense state. What does general relativity say about that beginning point itself?
That's where things get tricky, and where GR starts to show its limits. In 1965, Roger Penrose used GR to prove that if a massive star collapses under its own gravity, it must inevitably form a singularity.
A singularity. What exactly is that?
A point of zero volume and infinite density, where the curvature of space-time becomes infinite. All the matter of the star crushed down to nothing. The known laws of physics break down there.
Okay, that's for a collapsing star. How does that relate to the universe's beginning?
Well, in 1970, Penrose and Stephen Hawking essentially reversed that theorem. They showed that if general relativity is correct and the universe is expanding as we observe and contains the amount of matter we see, then tracing that expansion backward in time must lead to a Big Bang singularity at time zero. The entire universe must have begun from such a point.
So GR predicts its own downfall, in a way. It predicts a point where its own equations stop making sense.
Exactly. The singularity theorem showed that GR is incomplete. It cannot describe the very beginning. To understand the origin, you need a theory that combines gravity with the physics of the very small. You need a quantum theory of gravity, because in that incredibly tiny, energetic initial state, quantum effects must have been dominant.
Which brings us neatly back to that central conflict we started with, and also to black holes, the other place GR predicts singularities.
Right. Black holes are the ultimate testing ground where gravity becomes incredibly strong, potentially revealing clues about quantum gravity. The basic idea, as we mentioned, goes back to John Michell and Laplace in the late 18th century, an object so dense that its escape velocity exceeds the speed of light.
And GR describes how they form from collapsing massive stars.
Yes. When a star much more massive than the sun runs out of fuel, the outward pressure from nuclear fusion stops. Gravity takes over. If the star's core is above a certain limit, the Chandrasekhar limit, even the quantum pressure from electrons or neutrons can't stop the collapse. It crushes down towards a singularity.
But the singularity itself is hidden.
It's hidden behind an event horizon. This isn't a physical surface, but a boundary in spacetime. Once you cross the event horizon, the curvature is so extreme that all possible future paths lead only inwards, towards the singularity. Escape is impossible, not even for light. The source material aptly quotes Dante. All hope abandon, ye who enter here.
That's chilling. What would it actually be like to fall into one? Does it depend on the size?
Very much so. Near a relatively small, stellar mass black hole, the tidal forces are immense even before you reach the horizon. The gravitational pull on your feet would be so much stronger than on your head that you'd be stretched vertically and squeezed horizontally, like spaghetti. It's called spaghettification.
Not pleasant. What about a supermassive one, like at the center of a galaxy?
Those can be millions or billions of times the mass of the sun. Because they're so much larger, the curvature at the event horizon is actually much gentler. You could, in principle, cross the event horizon of a large supermassive black hole without immediately feeling anything dramatic. The tidal forces only become lethal much closer to the singularity, maybe hours or days later, depending on the size.
Okay, so black holes exist, they trap everything. But then came a paradox involving thermodynamics.
Yes, a huge one. In the early 1970s, Jacob Bekenstein suggested that the area of a black hole's event horizon is a measure of its entropy, its information content, or disorder. But a fundamental principle of thermodynamics is that anything with entropy must also have a temperature, and anything with a temperature must radiate energy.
But black holes, by definition, don't radiate anything.
Right.
That's the whole
Exactly the paradox. If Bekenstein was right about entropy, black holes must have a temperature and must radiate. But if GR's description of black holes was complete, they couldn't radiate. It seemed like a fundamental contradiction.
How was it resolved? This sounds like another clash between GR and something else.
Quantum mechanics again. Stephen Hawking found the resolution in 1974 by considering quantum effects near the event horizon. Quant theory tells us that empty space isn't truly empty. It's filled with pairs of virtual particles and antiparticles that constantly pop into existence, exist for a fleeting moment, and then annihilate each other, borrowing energy from the vacuum according to the uncertainty principle.
Virtual particles.
Yeah.
Like temporary ghosts.
Sort of. They're usually undetectable because they vanish so quickly. But near the intense gravity of a black hole's event horizon, something amazing can happen. Imagine a virtual particle pair pops into existence right at the edge. One particle might have positive energy, its antiparticle partner negative energy, which is allowed for real particles inside the strongly curved space-time near a black hole.
Okay.
If the negative energy particle falls into the black hole, it effectively reduces the black hole's total mass and energy. Its positive energy partner, now stranded outside without a partner to annihilate with, can escape away from the black hole as a real particle.
So the black hole isn't radiating from inside the horizon, but particles are escaping from just outside, fueled by the hole's mass.
Precisely. To a distant observer, it looks exactly as if the black hole is emitting thermal radiation, just like a hot object with a specific temperature. This is Hawking radiation. It beautifully resolved the paradox. Black holes do have entropy, proportional to horizon area, and they do have temperature, inversely proportional to mass, and they do radiate thanks to quantum effects.
And smaller black holes radiate more.
Much more and much hotter. A black hole with the mass of the sun would have a temperature incredibly close to absolute zero. Its radiation would be undetectable. But a hypothetical primordial black hole, maybe formed in the early universe with the mass of a mountain, would be incredibly hot and radiate energy fiercely. The source suggests maybe 10,000 megawatts, like a power station. It would eventually evaporate completely in a final burst of radiation.
So black holes aren't truly black, and they eventually disappear. That connection between GR, quantum mechanics, and thermodynamics is amazing. It really pushes towards that unified theory, doesn't it?
It's one of the strongest hints we have. Finding that grand unified theory, GUT, that combines the electromagnetic, weak, and strong nuclear forces, and then the ultimate goal, a quantum theory of gravity that includes the fourth force, gravity that's the driving force.
Let's quickly recap those four forces.
Okay. We have matter particles, like electrons and quarks, which have spin 12, and force-carrying particles with integer spins, 0, 1, or 2. Gravity, mediated by the hypothetical spin 2 graviton. Weakest force, long range, always attractive, still haven't found the graviton. Electromagnetism, carried by the spin 1 photon, governs light, electricity, magnetism, chemistry. Well understood.
Then the nuclear forces.
The weak nuclear force, carried by heavy spin 1 particles, W and Z bosons, very short range, responsible for certain types of radioactivity like beta decay. Famously, it violates symmetries, it treats left and right differently, parity violation, and matter and antimatter differently, charge violation, and even the combination, CP violation.
That CP violation discovery was a shock, wasn't it? That the laws themselves aren't perfectly symmetrical.
It was profound. It might even be connected to why there's so much more matter than antimatter in the universe today. And finally, the strong nuclear force, carried by spin 1 gluons. This binds quarks together inside protons and neutrons. It's incredibly strong, but only acts over tiny distances within the nucleus. It has this property called confinement. You can't isolate a single quark.
So unifying these four, especially bringing gravity into the quantum fold, what's the leading candidate theory now?
The most developed, though still highly theoretical and unproven experimentally, is string theory. The fundamental idea is that the basic constituents of reality aren't point-like particles, but tiny, vibrating, one-dimensional strings. Different modes of vibration of these strings correspond to different particles. An electron is one vibration pattern, a quark another, a photon another. Even the graviton has a corresponding vibration.
Okay, sounds elegant, but doesn't it come with some unusual requirements, like extra dimensions?
It certainly does. For the mathematics of string theory to be consistent, it typically requires the universe to have more dimensions than the 3 space and 1 time we experience, usually 10 dimensions in total. 9 space, 1 time.
9 space dimensions. Where are the other 6?
The idea is that they are compactified, curled up incredibly tightly, on a scale far too small for us to perceive directly. Imagine a drinking straw. From far away, it looks like a one-dimensional line. but get close, and you see it has a second curled-up dimension, its circumference. The extra spatial dimensions in string theory are thought to be curled up like that, but on a vastly smaller scale.
And the way they're curled up affects the physics we see.
Exactly. The geometry of those curled-up dimensions is thought to determine the types of particles and forces we observe in our familiar four dimensions, the fundamental constants, everything. Which leads to this tricky idea called the anthropic principle.
Ah, yes. The idea that the universe seems fine-tuned for life because, well, if it weren't, we wouldn't be here to observe it.
Essentially, yes. If string theory allows for many different ways the extra dimensions can be curled up, a landscape of possibilities, maybe only a tiny fraction of those configurations lead to physical laws that allow stars to form, chemistry to happen, and ultimately life to evolve. So we naturally find ourselves in one of the universes compatible with our own existence.
It feels a bit circular, though, doesn't it? Is it really an explanation or just saying things are the way they are because we're here?
That's the big debate. Is it a cop-out or a necessary realization when dealing with theories that predict multiple possible universes or outcomes? It's definitely philosophically charged.
Speaking of philosophical issues, back to time, we experience it flowing in one direction. Why? If the basic laws are time-symmetric.
Right. This is the puzzle of the arrow of time. There seem to be three related arrows. First, the thermodynamic arrow. Time flows in the direction of increasing disorder or entropy. Things break, they don't unbreak. Scrambled eggs don't unscramble themselves. This is rooted in the second law of thermodynamics.
Okay, entropy always increases. What's the second arrow?
The psychological arrow. The direction in which we remember the past and not the future. Our sense of time's flow seems tied to memory formation.
And the source argues these two are linked.
Intimately linked. The act of forming a memory, whether in a brain or a computer, involves taking disordered components and arranging them into an ordered state. The memory. But storing that information requires energy, and the process inevitably dissipates waste heat, which significantly increases the total disorder of the universe. So the increase in order within the memory system is vastly outweighed by the increase in disorder, entropy, in the surroundings. Our psychological arrow points in the same direction as the thermodynamic arrow because memory formation drives entropy increase.
Mind-bending. Okay, thermodynamic, psychological. What's the third?
The cosmological arrow, the direction in which the universe is expanding rather than contracting.
And how do these all relate to the beginning, the Big Bang?
The connection comes via ideas like the no-boundary proposal developed by Hawking and Hartle. This uses quantum principles applied to the whole universe. It suggests the universe, when described using a concept called imaginary time, which we'll get to, might be finite in extent but have no boundary, no edge, and crucially, no initial singularity. In this picture, the universe must start out in a very smooth, ordered state. That initial low entropy state guarantees that as the universe evolves and expands, entropy will increase, setting the direction for the thermodynamic arrow.
And because life needs that entropy gradient to function.
Intelligent beings like us, who remember the past and rely on ordered processes, can only exist during the expanding phase when the thermodynamic arrow is clearly defined and points away from that initial ordered state. The three arrows align.
Wow. Okay, one last major consequence of GR before we wrap up. Time travel.
Yes, the sci-fi favorite. General relativity, surprisingly, does seem to allow for it, at least mathematically. Kurt Gödel, the famous logician, found solutions to Einstein's equations back in 1949 that described rotating universes containing closed time-like curves, paths in space-time that loop back on themselves, allowing you to return to your own past.
So GR doesn't forbid it. Is it related to faster-than-light travel?
There's a deep connection. Special relativity shows that if you could travel faster than light, you could also send signals or travel backward in time, leading to causality paradoxes like the grandfather paradox. The limerick captures it perfectly, arriving the previous night after traveling faster than light.
Could things like wormholes allow this? Those hypothetical tunnels through spacetime?
Wormholes are theoretical shortcuts predicted by GR-thin tubes connecting distant regions of spacetime, potentially bridging light years and maybe just millions of miles. If you could stabilize a wormhole and traverse it, you might be able to travel vast distances quickly and potentially, depending on how the mouths of the wormhole move relative to each other, even travel through time.
But we don't see tourists from the future popping up. So is it impossible?
Well, there's the chronology protection conjecture proposed by Hawking. The idea is that the laws of physics themselves conspire to prevent macroscopic time travel and protect causality. Quantum mechanics seems to provide a mechanism. Remember those virtual particles?
The ones involved in Hawking radiation.
Exactly. If you tried to create a wormhole stable enough for time travel, virtual particles circulating through the wormhole's throat would become real and build up immense energy densities. This energy buildup, drawing on effects like the Casimir effect, which proves virtual particles are real, would likely become so intense that it would warp space-time violently and destroy the wormhole before it could be used to violate causality.
Nature slams the door shut, so time travel to the past is likely out.
The evidence suggests the necessary space-time warping hasn't happened, or physics prevents it. Travel might only be possible into the future, which special relativity already allows via time dilation moving fast, slows your clock relative to others. The past seems fixed.
Okay, what a journey. From perfect spheres to expanding universes, quantum foam, black holes that radiate, and maybe even curled-up dimensions.
We've gone from a tiny Earth-centered cosmos to this vast, dynamic, quantum-ruled reality where space and time themselves are relative and flexible. And we've seen how our two best theories, GR and quantum mechanics, clash, especially at the beginning and inside black holes.
Which brings us to that final, really provocative thought from the source material, connecting back to the beginning of the universe and the nature of time. General relativity in real time predicts that singularity at the start.
Yes, a breakdown point. But that no-boundary proposal we mentioned uses imaginary time in its calculations. And in imaginary time, the singularity disappears. The universe can be finite but self-contained, without an edge or beginning point.
Imaginary time.
Yeah.
What exactly is that? Is it just a mathematical trick?
Mathematically, it's what you get when you multiply time by the square root of -1. The weird thing is, mathematically, treating time this way makes it behave just like another dimension of space. So instead of 3 space dimensions and 1 time dimension, in the imaginary time formulation, you effectively have 4 spatial dimensions.
Okay, my head hurts a little. But what's the philosophical punchline?
The punchline is this. We think of a scientific theory as just a model, right? A mathematical description that exists in our minds to help us predict observations. So if we have 2 mathematical descriptions, one using real time that has a problematic singularity, and one using imaginary time that makes the universe mathematically complete and boundary-free, does it even make sense to ask which time is real?
Shane, maybe imaginary time is the more fundamental concept for describing the universe's underlying structure.
Perhaps. Perhaps what we perceive as the unidirectional flow of real time is just a consequence of how we, as complex beings within this universe, happen to experience and measure things. Maybe it's just a useful concept we invented to describe our corner of reality, while the deeper mathematical structure operates on principles that look more like space than time.
So the foundation of reality might be built on imaginary numbers.
It's a possibility that the maths points towards. Is the real time we experience fundamental or just an emergent property of a deeper, timeless, in the imaginary sense, reality?
That is definitely something to chew on. A fantastic place to leave this deep dive. We hope you enjoyed this journey through our evolving understanding of the cosmos. Thanks for joining us, and we'll see you next time on The Deep Dive.